Okay, so in this video, what we're going to do is we're going to look at a sheet that you should have on AC generation, or alternating current generation, and see how it works. So we got a little diagram here. We got a couple magnets with a coil inside, and we're going to talk about how this stuff generally works. So you should be able to just follow along with the sheet that you have, and everything should work out nice. All right, so here we go. So basically, an AC generator uses a rotating armature inside a magnetic field in order to create a current. So, of course, the armature is the squarish-looking thing here. We've got the blue and red magnets. We've got a couple of rings here, and those are called brushes, actually. We'll get to that in a second. But this thing spins around, usually using like water or something like that to spin with a turbine. But that thing spins around inside of a magnetic field in order to create current. Now, moving contacts called brushes touch what are called slip rings, which are part of the armature. So they're called slip rings because they are rings that slip. So the armature is actually attached to these metal rings. You can see them in the problem. And the little blackish box things, those are called brushes, which are actually in contact with the slip rings. And then as they're not like fused or soldered on there or anything like that. So the rings can actually slide, and they just keep sliding on top of them, or slip. And that's why they're called slip rings. So they're moving electrical contacts, and it's those brushes that actually wear away in things like electric motors and generators and that kind of stuff. Over time, they just wear away into a fine dark dust. And sometimes also they don't work anymore. It's because the brushes have been worn away. Okay. Now the same slip ring and brush are always in the same contact at all times, and they have a permanent contact with each one. So there's two brushes and there's two slip rings. Now if we map out the graphs a little bit, there's two graphs that we can make look something like this. And actually we lost, we'll make that so we can actually see the letters and everything like that. Maybe that's a little better. We got two graphs we can make. We can make a flux graph and a voltage graph. And we got, diagram A, B, and C. We've got A, B, and C marked on our graphs. Notice that the flux, when the flux is at maximum at A, there's zero voltage on the voltage graph. And when there's zero flux on B, there's maximum voltage on for B. And that's because, remember, when we get induction, it's not about how much flux you have, it's about how much your flux is changing. So A, when it's the first picture there's lots of flux going through it. But if you just wiggle the armature back and forth a little bit, the flux isn't going to change by a lot. It's just going to be a little bit less, a little more. It's not going to change very much. But in picture B, the way picture B is set up, there's no flux going through it. But if you wiggle that coil, there'd be a massive change. And that's why maximum flux gives minimum voltage and vice versa. So it's kind of tricky, right? So when there is a flux at a maximum, there's no EMF being produced. And minimum flux gives maximum EMF. Remember, it's all about how much the flux changes, the delta flux, not the amount of flux, but the delta flux that's important, okay? So it's the change in, which is what we're talking about. It's the change in flux that's important, which is maximized when the coil and B are actually parallel to each other. So it's all about the change in flux. And that thing then spins around. I showed the animation for this in the previous one. That's how that works. Okay. Now, there's more than just AC. There's also DC, and this is a DC motor / generator, whatever you want to call it. And notice one of the biggest differences is you've gone from one ring to two rings, and that one ring. You've gone from two rings to one ring, and that one ring is split. Okay, and this is the big difference between AC and DC. And if you have to graph it out, it actually looks like this instead, where instead of having the same brush and same ring in constant contact, it actually switches. So right when the voltage is about to go negative, the two contacts actually switch, and the polarity gets flipped. And that's what allows you to have the voltage and current always being on the same side. So a DC generator or motor can be made by replacing the slip rings with what's called a commutator. So that's what that it's not a ring anymore because it's cut in half. That's called a commutator. And you sort of have switching contacts instead of having constant contacts, which is what you have with AC. So, down, here we go. The commutator allows the contacts to switch, so the same brush always keeps the exact same polarity each time. And that's the main difference between an AC and a DC. An AC allows the contacts to switch, where DC does not. And I think I showed this in the simulation in the previous video as well. But that's the basic idea behind it. Okay, so we go to the simulation for just a little second here. This is simulation for the AC generator. I think I've shown this to you before, but you can see, you got the two. Ooh, that's kind of weird. You got the two slip rings. You got the two slip rings, and well, the two slip rings, the two brushes, and the thing sort of goes around and goes around, and you can see where it's maximum flux, got minimum voltage, and vice versa. Now, if we want to switch this to a DC generator motor, that should be this one. Yeah, there you go. We've gone from 2 rings to 1 ring, and now you've got the commutator in there, and you can see, that black line is like a separation, and you can see when it goes around every half turn, the 2 brushes actually switch contact. So right when it's about to go to a negative voltage, it switches contact, so it always stays positive. So the voltage and the current, especially the current, is always going in the exact same direction, especially really important for like motors that are running things. If you're going to use a blender, you don't want your blades to be zigzagging or wiggling back and forth. You want them to go in one direction. So using a commutator allows it to switch contacts and have the current keep on going in the same direction. Okay, so let's see if we can do a little practice with the AC generators. So let's say we've got, just draw, we've got an AC generator, just practice using the expression a little bit. And let's say we've got 3,500 turns of wire. Let's say we've got a 4.5 Tesla magnetic field. And let's say it spins at, well, just really, really slow. I mean, these things spin really, really fast. We're trying to use low frequencies so the numbers aren't all over the place. Let's say it goes 0.35. No, we've got a 3 and 5 already. Let's switch that up a little bit. Let's use something else. 0.18 hertz. There you go, something like that. So we got 3,500 turns. It's a 4.5 Tesla magnetic field inside. It spins at 0.18 hertz. And let's say we've got a 1.25 meter squared area. Okay, and we are going to find out what's the maximum EMF this thing can actually produce. All right, no problem. Well, there's only one expression for this. EAC is the omega NBA sine omega t. That's how we can calculate AC EMF. Now the key right here, it says maximum EMF, and that's awesome, because if it says maximum EMF, we know it's going to be maximized expression. What we can do is we can get rid of this, because if it's maximum EMF, sine whatever is going to be equal to 1. So don't worry about it. You don't have to do anything else. Leave it alone. Just says maximum, you make it equal to 1, done. Don't have to worry about it. So all you're left with is the omega n, b, and a. Now, of course, the omega is 2 pi f. Okay, so we've got the 2, we got the pi, we got the frequency. It's going to multiply together. So 2 times pi. We'll multiply that by the frequency, which is 0.18. And we got about 1.13 radians per second. And this is the nice thing about the maximum EMF. You don't have to use the trig function, so you don't have to make sure your calculator's in radians instead of degrees. All right, so once we have that, the EAC is going to be that 1.13 multiplied by the n value, the b value, and the area sine theta is equal to 1. So get the 1.13. We'll times that by 3,500 turns. We'll times that by the magnetic field, and then we'll times that by the area, and we get a maximum EMF. We'll round off a little bit, but it's like 22,250 volts. I'm hoping that's all good. Or you can say around like 22 kilovolts is what would it be. And there's your maximum EMF. So, I mean, it looks like a really crazy expression, but often sine theta is equal to 1. You got that maximum. Having that maximum just makes it so much easier. And then you sort of plug and play a little bit. And you don't have to worry about your calculator being in radians. Okay, so that is how we can calculate the maximum EMF from an AC generator. And then what you could do is you could attach this to like a transformer and then use it to do transformer calculations.